Okay, so welcome everyone to this new episode of EagleFly, the experimental debugger. Today we will continue making this awesome debugger, and if you'd like to follow along, please don't hesitate and be welcome. With that said, I would like to start by opening the project. Please, if you have any questions, you can post them on Twitter or YouTube and I'll be there to answer. With that said, I would like to see where we left off, which if we compile, I don't know if we compile at all. Okay, so that seemed to work. And the thing that we are doing right now, what the last thing we did was we started decoding one by Opcode instructions, which is this table. Let me go to the here you go. So this is the table, opcodes are a bunch of tables that basically store their way, basically are like a bunch of tables that pretty much tell you which instruction you are, it's encoded, And among that you have the other stuff like the mother M bytes, SIB bytes, displacements, intermediates, prefixes as well. So this is a whole set of things that we had to do. And the first thing we did yesterday was that we found out, well, we set up this. Right now we are not parsing prefixes, which is this part, because we're gonna run, for simplicity, we're gonna assume that each instruction is one, but an opcode, and two, with not prefixes at all, So it's this kind of weird opcode table, or this opcode instruction set, which doesn't has too much of it, but it's for starters. It's the first thing we're gonna do. So the first thing we're assuming here is that, hey, we got the opcode by, we know that we find it, we know that it's there. So now I want to go and find the opcode table. I believe, yeah, we have a mnemonic, that's like an intermediate step working with it. So we define a mnemonic and we decode the opcode, basically. It's like, hey, I want to store the mnemonic somewhere based on the opcode that you tell me, and we input the opcode and we get the mnemonic. Pretty straightforward. And I believe if we are, we have this problem. what are we looking here? Oh, okay, yeah. Oh yeah, the point here. Let me try to find it, because why not? Uh, formatted format strings. I have to save this one because I use it a lot. Okay, so the symbol I'm looking for, it has to be this. Alright, so it's the module 0F5. Okay, so basically okay. So something like this, and there you go. So we're printing the mnemonic now that we found it, and the next thing. Well, now we have two clues in here. Once is then the instruction itself that we are printing here that we've already gotten, but the instruction is not just the mnemonic. Instruction has operands, and these operands have a certain encoding as well. We have certain clues to find out which operands we are targeting, or which operands are encoded inside the instruction itself, and those are encoded in the motherboard byte, and if any, in the SIB byte and subsequent bytes in the immediate and displacement as well. So all this information will tell us the complete information to find out which operand we are looking at. So that's why we set up this kind of for loop in here, where the whole point of this is that, well, we found that, we already know that. And we try, well, we get back a series of information, for example, the operand count, and we're going to iterate on, we know that how many operands we have, which is basically this idea here, where, for example, here we have 2 operands, and each operand is encoded in this with this format, which it's encoding for the table with specific. I don't remember what it was. B is a byte, so this means it's a byte, and it can be a register, it can be memory. And G, I don't know, it also tells us something, but it's also a byte. And we have several ways. So we have 2 here. Here we have these REX prefixes. Here we have these conditionals. For example, here also we have 2. Here we have, for example, this is special. We have 2 operands, but the first operand can be AL or R8. L. And yeah, so there's a lot of it. The gray ones are special ones, which in this case means that, well, it's 1A, so that means that they encode the there's a register extension code in the mother and byte reg field. So this is special information. Right now we're not gonna care about that. So yeah. So with that in mind, we know how many there are. Now we have to find which are. And for that we define here some special enum here, which we tells us the addressing modes, and the operand types. Which operand types are pretty much simpler than to do. But for example, let's start with this. We can say something like So the thing I would like to do now is try to simplify this a little bit, because now think about it. I mean, there are certain repetitive cases here. I mean, they probably are telling me something. I mean, they are telling me different special case scenarios. For example, the first one tells me that there is a direct encoding after the main opcode, so we have to go forward and inspect that, to find it out. But and also as well we have in any other cases here, for example, I believe only on no mother RAM there's no mother RAM. In the others we have RMMX. I mean, most of the time we're gonna go and find. I mean, we're gonna go and target the mother MI. Most of the cases. I mean, most of the cases in the sense of addressing most, not because in practice we're gonna find it, but uh, in practice can be any other case. You know, in practice we haven't found. We don't have the knowledge to thoroughly understand that part with the practice, but in case of the concept or the theory here is like, hey, we have a bunch of this information. You know, most of them we're gonna go targeting it, so we can assume that we can go and try to find it, except for no mother M, I believe, or the direct address, for example. This is another one that we don't have. VXGPR. This is some. Yeah, this is also on the VX. This it does has a mother RAM. This does has a mother RAM. Mother RAM. Yeah, we has it. This is our flags, but I don't think. Yeah. Okay, so well, I mean, we'll probably so yeah, it doesn't matter. Let's try to do this stupidest thing possible and go one by one, just writing each case scenario, you know, because I mean, and later on we can see the semantics working, you know, so we can start compressing. But for now, we just want to see everything, you know, however it is, even if it's shitty or stuff. Um, yeah, it's gonna be a good thing. Now, for example, direct address, well, that's a kind of special one. It's kind of simple. We can say that we got the operand, and we have, I believe, Sastan Kyoko. call him an opcode, but I prefer one by. I think it's the same. So in this case, we're gonna get a car, and this let's call it by. We don't know what it is. Well, we believe it's immediate. Which size we don't know, because for that we need to get the type. So probably it's good to say let me think about this. I mean, we can have a switch we can have a switch inside a switch, but I don't think that would be a good thing. Let me think about this. So we have a type, and let's say we have, I would like to say something like this: convert type get value type, how can I say, get byte size and probably, I mean, we can do this in here because and we can say, hey, for byte size, and then we can say, hey, we got a byte size, so we can pretty much move and probably I want to say, where is it? We have the current opcode byte here, so we're assuming that the opcode byte is on the mnemonic, and I want to keep it there because it's gonna work pretty much better if we keep it there. One opcode, one byte opcode, it's in there, and I would like to say here that we got another one here. That's gonna be operand fetcher, something like that. And we want to have an operand fetcher, one B opcode, you know. Well, I don't want to move the one B opcode, something like that. And then we have that, we get by size tab, you know, we get the size, operand fetcher is going to be moving. So we get the operand fetcher, we don't need this. And we can say, we can have a loop here. In this case we don't need a loop probably because we just need a casting. Now we have to be really careful about this because we can have different endianness, and depending on the endianness the data is going to be different encoded. So right now we're assuming where we can say if arc little endian you can say this, I mean we want to transform everything to little endian, I guess. I think it's proper, So probably we can say if arc is big endian, we're gonna do something special here. So probably, in big endian, the least significant bit is the last bit, and the first bit is the most significant bit, I want to say change endiness. Or convert big to proper is not an operand fetch. Well, this is the operand by current by, I'm gonna call it. Since we don't know exactly what's gonna be in there, I can say current by or C by. Okay. I want C by. I want this byte size. Okay, we can get the base and start working on, or we can start from the base that we assume it's the base, yeah, probably, I mean, in any other case, we could probably want to have a buffer here, data buffer. We can say that we have something like that. Well, push array of a car to the, and we haven't thought about the, well, I'm gonna say the system state, the system arena. Let me think about if we care about the order of these pushes. I mean, this is totally transient information, In this case, probably, I mean, the mnemonic as well is not, we don't care, well, let me think about this. I mean, on the first glance, we think of the simplest and the stupidest thing about how do we want the parser to work and what's the output that is going to outcome, And I mean, most of it's going to be pretty much a text thing, Yeah, of course, I mean, probably we want to, let me, what to do here? Make run printf.s. We think about it like a printing stuff, like a dumper, boom, 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 boom. We just like, hey, we know that this is the data, we throw it back to the user into a file, into something, That's the simplest way to think about the disassembler. But of course, I mean, when we want to integrate this kind of information with the debugger itself, it's gonna be other kind of stuff, Because now, I mean, it's not just, I mean, we can leave it that way, which is a dumper, and we leave out all the data that we collected, which will be I don't know. I mean, I would like to reuse the data information that we already parsed, so we don't have to process it twice. if we need to use it. I mean, if we need to reuse that data. So, for example, yeah, I mean, the debugger probably and the tracer itself wants to have all that information. So every time, for example, one thing I was thinking about, this is not for right now, but probably the tracer is gonna be really really helpful to disassembly assurance, you know. But I mean, like, hey, we're probably gonna get some errors by the disassembler itself. So it would be nice to like runtimely, you know, in runtime execute these instructions and see how they operate, you know. So see like, hey, we are assuming this is my guess. This is a move instruction, you know. So we disassemble that and we pray it out, and then we run it, and we saw that this not. We found that that is not the instruction that we thought it was. So with that, now we have a pretty sure. I mean, we have to emulate like pretty much each instruction. In this case, we don't have to emulate because we are running on the same architecture, but normally we have to we'll need to emulate the instruction, so we have like a more assurance that the instruction that we disassembly by this method, that it's pretty much reading the Opcode bytes, which is a more static way to do it. We accompany it, we assure it with a dynamic analysis of the outputs, you know, which I mean is gonna serve for this assembler and it's gonna serve for the tracer itself, which is basically the idea of tracing data information that the instructions execute. So yeah, I mean that's for the future, but I mean it's just something to consider because if information that we found out here, it can be truly truly important, you know, and we can probably save it somehow or give it out to the tracer if it's needed, you know, in polling packets, or you know, so some way to let them use it. For now, I don't know how much of it. I mean, we're not gonna implement it, but let's just try to leave these spaces so we can easily in the future try to find a way to do that, you know. So if we do this completely on land, yeah, we have a buffer, you know, we push array with a car, this is a marina, and we have a size of it. We can say, hey, we have a byte size, and this is byte size completely on endian data buffer. In this case, we know this is a source this byte size. Boop, boop, boop. All right. And this is pretty much I mean this is a black copy in the other way around, but it's good to have it, I guess. What else? So now that we have that information, you can see we're gonna work with the image buffer. Now that's an immediate. We have the data now transformed into appropriate little endianness, and we can work with it. In this case, It says something like that, I guess. This is an integer. I can cast it. So probably since we don't know the type, well, we do know the type. We know the byte size. We can have something here. For example, I was thinking like, hey, we want a type. We know we have a type information. How can we do this? Which are the types that we have? Hold on a second. Okay. So we know the type of it, but one important thing to think about is like we want to refer to it in different manners. For example, since it's in memory, I mean, if data it's in memory, I mean, we don't need to represent. Well, for example, for the immediate, probably it's good. But we don't need to think it too much, you know. I mean, because the data it's in there, you know, we don't have to think about, hey, we place. I mean, probably they convert to little endianness. It's good in certain points, but we don't need to cast it or have any kind of special data. You know, we can say, hey, whatever is in there is treat me like a car. You know, I'm gonna print it out as it if it was. You know, so I can even, I don't know, and I'm gonna print the bytes one by one. You know, pretty straightforward. And that's it. For now, it's gonna be something like that. byte index 0 duty index less than byte size. Byte index. And I believe I know where is it. We have in the PDF file had information about if it was beginning, yeah. I believe it was deprecated. I don't remember. Yeah, it's deprecated. Yeah, because this is the whole thing, you know. This is for the image file itself. But the target architecture, I mean, we can have I don't know. I don't know. I mean, my question is, I mean, we have a P file, you know, that it's labeled endian. But the text section, it's beginning. Is that possible? It would be pretty much weird. Because if you think about it, I mean, the whole set of architecture, it's meant to have the same, you know. So just let me look at it, you know, so we can think about it. Beginning machines. Okay, so for example, the x86 and x64, it's, I mean, which are the ones that we are like targeting right now, are the ones are all little endian, so we don't have to think too much about it. The beginning architectures include the C architecture, Freescale Coal-Fire, the Motorola 68000 series, the Microblaze, and the ABR 32. So yeah, I mean, there are not a lot of them, but well, what can we trust about Wikipedia? Assembly language, optimization. So yeah, I mean, probably we well, right now we don't care too much about that, so we can even go without it. So we have that. I can say space. And this is a string. I can say hey. Well, if this is a car, probably it's gonna work, but I can say something like that. For BX, we don't care right now. For addressing mode, right control. Let me think about this. This has some other RAM, so we have to go and find it. Probably, let me see. Select a control register. So this is the RAM. And the mother RAM. Get the rec field from the mother RAM. we just need like a shower, but for now. In 32T, rec. And there's a special coding here, you know, we have we can say something like, this is a 3-bit field, you know, and each one, if you remember, it was something like, where is it? Water ramp, side beam, here you go. So for example, the rec can be any of these values, and yeah, I mean, we pretty much have to find out which of these groups they are, you know, so we can have we can have like the pretty much stupidest thing here, you know. We can have a table, because I believe that tables are the best thing in this case. For example, if we go to the parser.h, you can even define it right now in here. I don't think there's a bunch of craziness going on here, but for example, we can say that we have here a field table. So it's going to be 256. I believe there are 256. I don't know. There are 5 times 8 are 40. We're looking here at 40, but this is because of the encoding in the rec. If we want to, yeah, but remember that with extension we have another problem. So we probably want with extension would be, we have another 4-bit 2 to the 4. It's 16, but so we have 16 groups, isn't it? So it would be like 90 fields. I don't remember. It was, let me see. Right here we have it, you know. We have on the rec field R gets expanded, and now we have 4 bits, which is gets us to 16. And with that we can now access to the upper extended registers on i32e mode. Such registers are not encoded as here, you know. For example, this is interesting. We have, I mean, we have extended ones, which is not just the, R R8 through I15 through R8 through R15, which are the extended general purpose registers, but also we have access control registers as well, like CR8 through CR15 and debug registers DR8 through DR15, which normally we don't care because we just need to access CR8 for the controls. But in general, I mean, the thing that I want to find out is like, how are they encoded? I mean, are they like, and I believe we have a, it was a direct mapping, you know, I do remember. It was, there was a direct mapping. I mean, in the table that we had before right here, this is for the SIP. The SIP also gets extended, you know. It can be also be extended for its base and for the index. And but for example, here we are accessing, I mean, from EAX, you see here EAX jumps to MMO, you know, as if the encoding was, I mean, we jump RAX and all that stuff. So my question is, what happens to RAX? I mean, we know that RAX gets formed by the next bit set, you know? So probably what that means is that if you want to access RAX, you just need to set the R flag on the Rex register. I will imagine something different because no, I don't think so. Well, no, it should be something different. But Um, so yeah, I mean probably is because I mean if it's a bit set, we are accessing to basically. I mean it's pretty straightforward, I guess. Right now, well, for your rack, and probably for the others, probably are the same. I mean, if you, for example, you have a big set on R and all your bits are 0, you probably are accessing to R8, and just as well, if you go from R8 to R15 in the same sequence, in the same order. So yeah, I mean, if that's not the case, well, we have to find out. So we can say, I want to have something like, let me see. This is the addressing, these are the superscripts, and these are the other nodes. So I have to go this table. Basically, I want to copy all this. don't know if I can put, I can say something like this, I guess. And this is the extended ones with REX. Now, so probably this table can't work for any rate. I mean, for any register indexing. I mean, it doesn't has any order or any special thing here. Now, the format, I believe, has a core value. I'm gonna call it that's okay. Okay, so printf the rest. Let me see the problem with them. Okay, and get printf. Where's the printf? have get rec field from mother RAM. You can also implement that. Okay, so if we have the rec field, now we can just say that we are gonna find it, from the rec field table. And I can call this just register table, because I mean it's not, yeah, so we don't get confused. This is more like a generic register table, which we don't have the whole set of them. It would be nice if you just boom 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 continue doing this, like with control registers, debug registers, and the whole stack layout for all the registers that we can code, which probably we're gonna go with that. We're gonna do that, but for now I'm just gonna leave it like that. So let's encode it, and you think about it, well, if we go here, I mean the reason, well, from here to here it's something that IA32 encoding can go into it. From here to here, this is extra that they are used by RE, that they are expanded just if we use REX prefixes. So we can say that the rec field is going to encode so probably we want to have a way to instruct this a little bit simpler, which we can do it, I believe. I mean, these are the types that are encoded inside it, but we by no means we don't need to use these encodings at all. So that they pretty much along its way define the type, you know. I mean, we can have like a commenter part for this one. And this is gonna be I don't know, byte word mmx xmm. Well, mmx is the same, so probably this xmm, ymm, cmmm. And the whole point of this is to have probably this to be more like this instead of this one, because even though I mean this is gonna be like our intermediate mode access to the byte table, because that's the way that Intel encodes it. But for simplicity, this is probably we're gonna change back to this one later, but for now I just want to see it just by its size, so we cannot depend too much about because this has with this we can pretty much go straight forward and use the table directly, which is nice. So we will see. For now I would like to use it that way, so we just need to have some offsets from the baseline. So for example, we have a rect table, and this is gonna be register rect name. I can call this rect name table. Register rect names table. And then we got the rect field, which selects basically on Y. We move on X the same amount that we need, and then from byte size we allocate and we move on to the So what I would like to say here, where is it? Byte size I mean, it can be, this can be can even be this. If I code size operand, if I operand types, and the operand type can be worked out like this. Now let me think about why do we have that encoding. Is there a special reason why did we did that? Because the operand is constructed based on the decoder here. So the decoder is in charge of getting up the mnemonic and the type. So we can get it pretty much the same way. Yeah, because you remember, I mean, the types, where is it? Most of them behave the same way. Now the only problem, I mean, this is just because it's adhering to the operand size attribute, you know. I mean, it's adjusting itself to fit into this rule. So, but we can find the operand. Well, yeah, I mean, we need the operand size attribute to define it, but that's because of the REX and probably be with the some prefixes. So we probably need more information here. For example, get by size for operand type, and we'll get into, yeah, I mean, we need the type, of course. Well, you think about it, I mean, we don't need to do this if on the decoding step we do that kind of process. So probably can be 1B Opcode, cinematic up table mana, prefix list, you know, and the prefix list is gonna make for the types and encodings. So we get I mean, we can get pretty much, I mean, we don't need to do this like this. We just can say, hey, please get me the operand type. Operand type. And we don't need to do that, and this can be EagleFly, operand type, and we don't need to do this. Now the addressing mode, it has some special meaning. Yeah, I mean, the encoding, I want it to be a little bit different. I mean, I don't have any problem. I mean, since right now I don't have like this, like the whole picture for the addressing mode casing, I'm just gonna say EagleFly addressing mode, you know, operand addressing mode. And we can say, hey, you can say something like that. I prefer I want to play with the encoding, so it works pretty much better for ourselves. So yeah, so let's say we have something like that. I'm just playing around with this. We have rec name stable, and this is we don't have byte size anymore, so yeah, we have to, I mean, this is gonna be now type. There you go. Let me call it. It's gonna be better if I just say code. Yeah, I don't care about that. And this is open type. Go to prefix list. We have a D system state, and yeah, the prefix list is something that I have to do, but for now I'm just gonna say something like this. So yeah, I mean, this is more like what I want to do. You know, the decoded state option pretty much is the organizer for the disassembler. It's like, hey, construct me the whole set of information that from up to now I'm gonna start working with. You know, I like it pretty much better. It's a simpler way to do it. You know, operand address line. So yeah, so it's a kind of serializer point. What's the problem? What do we have? Oh. Yeah, so yeah, for that, if we want to do that, I would like to change this. What is this? No, it's not that. It's this one. Max instruction, operand count. So instead of having a car, thing I would like to do with this is that it's gonna start by 1. So this is UN32, and he believes that this is a type. It's a sign, which is kind of crazy, I guess. So probably I believe I can do it like this. And okay, so that's pretty much the idea of how, I mean, we want to start to play around with this. Now, for example, if we got the rec name here, we can say, hey, well, we want to print the rec name, you know. Bum. Some space in there, some, just want the rec name. Now this is important because if you remember the syntax, I mean, right now we don't care too much about that, but I mean, if we want to respect the Intel syntax for printing out, we should first, I mean, this is the first operand that we're gonna get. This is the source one, and as the source, it has to be to the rightmost edge of the instruction. So if we are looking at the assembly itself, right now we can leave it like that, doesn't matter. But I mean, every time we want to find an addressing, I mean, we search for the addressing mode, and we've tried to find out the way to handle it. You have to think the way to cache it, I guess, and then to move it back. So probably that we're gonna do that later, but for now I'm just gonna do that. You know. So I can do that, and then I mean we can go straight on through the whole thing. So let's run this. Let's see how much we've done with it. You know. And probably, I mean, for testing, the most stupid thing here. let me try to write something here. We have Fibonacci. And this is gonna be called let me think about this. For the message box one, it was pretty straightforward because, well, when I want to have like a playground with this. For the decoder, well, it's gonna have a bunch of stuff, but let me see if I can have a instruction that I can run. It's because all of them, well, no, not all of them, but for example, I can say there was this special case where we have for one by Opcode, I want to generate this instruction, this specific instruction. Let's say we have that, and we have here test, and this is gonna be run. So we can have well, this is totally weird. I can't say they are the same encodings, I guess. So we can say D, I guess, and I can so I can say XOR EX. So I clear it down, and I just move blah blah blah, and then probably I want to have the same layout as this one. I don't want to print anything, but just for starters, I can say something like that. Now where is it? It was here. I want the types. Where is it? And I closed the one that was important. Probably I can find it here. No, it's not this one. It's this one. Well, I can say this, I guess. build process, I can say that I want to compile this one. This is gonna be called some code instruction opcode and code. Opcode and code. There we go. There we go. Line 126. Syntax error in instruction. Oh, this is because I know value. Is that the problem? Yeah, it's a reservoir. Okay, there you go. And I believe this nonsense. If I go and open the listing, let me see what we got. We have an XOR 3360 and 0305. There you go. This is the value that we want, and this is the immediate mode of it, and we call exit process. Now the value, it seems not to be added, I believe. Because it should be an offset or 32, I guess. We have an R here. I don't know what this R is, but we have the proper encoding for that instruction. And for example, yeah, I mean this is encoding. So that means that we have a 32-bit displacement that follows, which is 000H. The reg opcode portion of the modern bits. So yeah, that means that we have EAX. And so if we, well, we can disassembly. There you go. So pretty much, yeah, we have an XOR and add. Okay, perfect. Yeah, we have, yeah, this assembly is pretty much better. We have a door. That's this one. This is the 32 dimension. This is the offset, pretty much. So from this instruction, well, I don't know, it's little endian, so it has to be 2FE8. Let me see. From my calculator. I'm gonna go to hex because that's the thing, and that's the thing. We have 2FE8, okay. 2FE8. It's that. I mean, that's the offset. And then we have a call. Now this, I want to see this value here, you know. This value is somewhere in data. It's a little bit upper in the instruction. This is 1401, so it should be lower down. So whenever we access it, we're gonna move by that opposite. So that means that if we but I don't know if it's relative to the instruction. This is not relative to instruction, I guess, because if not, we would know that. So this offset here should be from somewhere, isn't it? From some base. So what's the base? Since it's x64, it has to be 0, isn't it? It has to be 0 base and move from, I mean 0 base from image, I guess. So from the base of image, it's gonna move this offset and gather it, I believe. But of course, I mean, this is totally different, a totally different number. So I don't know what this meant. Yeah, I mean, we have to understand a little bit more. I mean, these are addresses, so we know, but this is an address from the, I mean, how does the encoder, or the disassembler, find out, how did he find out this value? Because it's not encoded here, you know. I mean, yeah, we have the offset here that is blah, and 14 auto blah 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 is way much bigger. So is the displacement, I mean offset and displacement probably denotes the same thing here. So we have a 32-bit displacement of data, but it's not related to the instruction pointer because that's something different. This is for IF32 encoding, so we don't have that kind of possibility. We do have it for if we specify it somehow, but this is not the case. So this displacement has to be added to some base. For example, this is added to the index. So the displacement is added to the index. Which, I mean, I believe is the SIB by. Or probably it's not. I want to see, can we see the data layer? I mean, this is the instruction one. Now dumping headers. Boom. Okay. We have a section header for, this is the I data, this is the data. So look at this. So this is more like a file pointer, isn't it? It's not the real pointer, this is a file pointer. It's not a memory pointer more. This is our data. So yeah, I mean, look at this. This is like the range that where the data that we're looking at is into. Size of raw data 200, file pointer to raw data, to location. This is a file pointer. Number of locations, number of line numbers. Flags initialized data rewrite. Okay. Okay, it's good. It prints the whole thing here. Okay. Initialize data is clear the board read only. So yeah, it should be data, and this is the offset that we are looking for. So this is 140004. Yeah, I mean, basically it's a file pointer, and it's basically the first data that we are accessing, you know. I mean, I can even copy it, so we can be sure of it. I copy that. And copy that. So yeah, it's the same volume. You can see here. So yeah, I mean, we're looking at the data itself, and it's a file pointer, so this is good to know. So I mean, yeah, I mean, it makes sense. I mean, it's good. I mean, since we are not running the data, we are just statically analyzing it. It's sufficient to see. I mean, it's just a property to point to a file pointer. So if it's a file pointer, it's not it's not an RBA. It's a file pointer from the base of the image. Okay. And for being sure, I mean, just because I wanna clarify my mind with this. We are inside here. This is the beginning stuff. I don't care about that. We want the section headers. Here we go. Go to the first one. We'll go to the here. Okay, so yeah. Okay, so yeah, it's relative to the image base. And for being sure, I mean, we're gonna test this. I don't know if we do have time right now, but we have now the test, and we can go and, I mean, we're gonna go and parse the PE file. We're gonna go directly to that data, and we're gonna see that, you know. So this is the pointer relative to the image base, and yeah, the pointer relative to the image base. Okay, so yeah, I mean, we set up for a little nice try. I mean, it's super I mean, this is nothing, but I mean, we're gonna get to something, you know, step by step. So I think we're gonna stop here, but if you like to have any questions or ask any questions, you please ask them, because I'll be there to answer any of your questions. And yeah, you can post them on Twitter or YouTube, and I'll be there to answer. With that said, I will stop here, and we will continue on the next stream. See you all, and take care.